Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, my name is Rayya Lintang with student ID 2025-32015 from Information System Class A. Today I will explain about order of growth theory and about the practicum. I will explain about these four. First is order of growth, second is big O notation, third is big omega notation, and the last is big theta notation. First, the order of growth. Order of growth is a measurement used to determine how the performance of an algorithm increase as the input size grows. This concept helps programmers compare different algorithms and choose the most efficient one. When the input size becomes large, an efficient algorithm may become very slow, while efficient algorithm can still run quickly. To express algorithm, there are three asymptotic notation. There are big O notation, the second is big omega notation, and the last is big theta notation. Okay, first is the big O notation. Big O notation is used to describe the upper bound or worst case scenario of an algorithm. It tells us the maximum time an algorithm might take as the input size increase. Big O is important because it helps predict how an algorithm behaves when handling large data. Rules of Big O. First, ignore constant. Second, take the highest degree terms, and the last, ignore smallest term. This rule helps simplify complexity analysis. Okay, we move to the third. Big omega notation is used to describe the lower bound or best case scenario of an algorithm. It represents the minimum time required for an algorithm to execute. Big omega helps us understand the best possible performance of an algorithm. And the last is big theta notation. Big theta notation describes both upper bound and lower bound. It gives a more precise description of algorithm complexity. And when n becomes large, algorithm B is much faster than algorithm A. Therefore, understanding complexity helps developers to make better decisions. Next, we move to the practicum. In the program, we define two functions. The first function represents a linear algorithm. This function uses a loop that runs from 0 to n, meaning the number of operations increase directly with the size of the input. If the input size doubles, the number of operations also double. This is why it is called linear complexity. The second function represents a logarithmic algorithm. Instead of iterating through all elements, this function repeatedly divides the input value by 2 until the value becomes 1. This approach significantly reduces the number of operations. Even if the input size becomes very large, the number of operations increases very slow. This is why logarithmic complexity is considered more efficient than linear complexity. Next, we move to the second practicum. First, we prove that n belongs to O n squared according to the definition of big O, and function fn belongs to O gn if there exists positive constant c and n 0 such that fn is less than or equal to c multiplied by gn for all n greater than or equal to n0. In this case, fn equals n and gn equals to n squared for all n greater than or equal to 1. N is less than or equal to n squared, therefore we can choose c equal to 1 and 0 equal to 1. So we conclude that n belongs to O n squared. Next we prove that 1/2 times n minus 1 belongs to O n squared. First, we expand the equation into 1/2 squared minus 1/2 n. The dominant term here is n squared because it has the highest power. In big O analysis, we focus on the dominant terms and ignore smaller terms. Therefore, this function belongs to O n squared. And move to the third. The third proof is 100n plus 5 belongs to O(n)2, O(n) square. This function consists of a linear term and a constant. As n increases, n squared grows faster than n. Therefore, the function can be bounded by a constant multiplied by n squared. We conclude that 100n plus 5 belongs to O(n) square. The fourth proof is 2n square plus n plus 6n plus 1 belongs to O(n) square. The dominant terms in this function is 2n square. Okay, the fourth proof is 2n square plus 6n plus 1 belongs to O(n) square. The dominant terms in this function is 2n square. The remaining terms 6n and 1 become insignificant for a large value of n. Therefore, the function is bounded by n square and belongs to O(n) square. And the last is 6 times 2 to the power of n plus 2n belongs to O(2n). Exponential function grows faster than linear function. Therefore, the dominant terms is 2 to the power of n. The function belongs to O(2n). In conclusion, all the functions have been successfully proved using big O notation. Big O help us to understand the program, understand the algorithm, efficiency, and compare performance. That's it for all. Thank you.